Good afternoon, students. In the previous lecture, we have studied the dielectric, the difference between the dielectric and insulator, and finally, the dielectric is nothing but it is basically an insulator, right? With some different physical characteristics that we have seen. Then we have studied the properties of dielectric materials. Then we have solved few numericals, and we have seen the boundary conditions for perfect dielectric materials. Just to recall the boundary condition between conductor and free space, just I will list out. Just recall, we will try to recall. Okay, first, a tangential component. What we got? Et equal to dt equal to 0, right? Then normal component, dn equal to epsilon naught en, that is equal to rho s. This we have seen, right? So this is the tangential component and this is the normal component. This is for conductor to free space boundary. Then next, between two perfect dielectric materials, right? So just I list out the boundary conditions. The tangential component is continuous, E tan 1 equal to E tan 2. Then in terms of d tan 1 divided by d tan 2 is equal to epsilon 1 by epsilon 2. This is a tangential component. Then second, the normal component, we'll see what is that, dn1 equal to dn2. Right here, the normal component of electric flux density is continuous, right? Then what about this epsilon d equal to epsilon e, right? Epsilon 1 en1 equal to epsilon 2 en2, right? This is normal component. Okay, this we should be knowing, right? Okay, we have seen the derivation. Next, in today's lecture, we'll see the refraction of the electric flux density d at the boundary between two perfect dielectrics, that we'll see. Then the numericals based on that. Then capacitance, that is capacitance, then parallel plate capacitor and several capacitance examples. If time permits, we'll see, or else we'll stop here, right? Okay. Yes. We'll take up the first topic, that is refraction of the electric flux density d vector at the boundary, right? So this is the boundary, right? Then in region 1, it is having the dielectric material having permittivity of epsilon 1, and region 2, it is having the dielectric material having permittivity of epsilon 2. And here one thing what we are analyzing here is epsilon 1 is greater than epsilon 2, means the permittivity is larger in region 1 as compared to the permittivity in region 2, right? This, assuming this, we will continue. And we have seen the boundary conditions, just I have listed out, right? Okay, just I have listed out, right? This one, dn1 equal to dn2, E tan 1 equal to E tan 2, right? These boundary conditions, right? You can observe here the electric flux density in region 2, it is making angle theta 2 with respect to dn2, right? And it is, and you can observe in this media, that is in the region of permittivity of epsilon 1, it is making angle theta 1 with respect to the normal component dn1, right? d1, right? This is d1. So you can observe here theta 1 is larger than theta 2. Theta 1 is larger than theta 2 because this is having the higher permittivity, right? So there is more refraction, right? So epsilon, since epsilon 1 is greater than epsilon 2, this you should be having in the mind. Is it fine? Okay. Then we will make use of the boundary condition. One of the boundary condition we have dn1 equal to dn2. This we know. The same thing. What is dn1? So I want dn1, right? So d1, take the projection of this d1 vector on to dn1. So what is dn1? d1 cos theta 1. So dn1 equal to d1 cos theta 1. Only they have taken magnitude, right? So dn1 equal to d1 cos theta 1. What about dn2? If I want dn2 is here, right? So d2 cos theta 2. So d2 cos theta 2 equal to dn2, right? I can write this, right? Fine. Then next, we have another boundary condition, right? D tan 1 by D tan 2 equal to this we have, right? D tan 1 by D tan 2 equal to epsilon 1 by epsilon 2, right? This we have. What is D tan 1? Tangential component. This is D tan 1. So I want the projection of D1 onto D tan 1, right? So D1 sin theta 1. So d tan 1 is nothing but d1 sin theta 1, right? Then what about d tan 2? It is d tan 2 is here, so actually d tan 2 will come here, right? But parallel to this we'll take here, right? D tan 2 is here. Then we want d tan 2. How to calculate this d tan 2, right? Similar to this, right? I will, instead of taking here, let me take d tan 2 here, right? D tan 2. Then what is d tan 2? d2 sin theta 2. d2 sin theta 2. Is it fine? Okay. Then cross multiply epsilon 2 into d1 sin theta 1 equal to epsilon 1 d2 sin theta 2. We have, let me, they have called it as 35. Let me use the same equation. This is equation 35, equation 36. Actually, 1, 2 I should have called. Then divide this equation 36 by 35. So I will be getting this equation. Tan theta 1 by tan theta 2 is equal to epsilon 1 by epsilon 2. But keep in the mind that epsilon 1 is greater than epsilon 2, right? So with this diagram in the mind, we will consider all these equations whatever we have written. Okay, then these few equations are given. Just will there is a derivation, but we don't have derivation. Just will take this how to remember, I will tell you, right? So how to calculate the electric flux density in region 2, that is d2, how to calculate, right? So that we'll see. This is from equation 35 and 36 only, right? But we don't have any derivation. Directly we'll see how to remember. d2 is equal to d1, fine. So root of cos square theta 1 plus sin square theta 1. For sin square theta 1, just epsilon 2 by epsilon 1 whole square. You just remember only this equation, then you can write this equation, e2 equation. Just only remember this. From this you can get this. I will tell you. So d2 equal to d1 under root of cos square theta 1 plus sin square theta 1. You write it. For sin square theta 1, you multiply epsilon 2 by epsilon 1 whole square. Then how to write e2? e2 is equal to, just instead of d1, write e1. Cos square theta, sin square theta. Sin square theta, cos square theta. Just reverse it. Epsilon 1 by epsilon 2 whole square. Right? So just only remember only one equation so that we can write it. Okay, when d2 will be equal to d1 whenever theta 1 is equal to theta 2, right? So d2 will be equal to d1 whenever theta 1 and theta 2 are 0, right? And one more thing, the d is means the refraction of d is larger. The refraction of d, right? The refraction of d is larger in the region of larger permittivity. And the refraction of E, opposite to this, the refraction of E is larger in the region of smaller permittivity. Just the opposite, right? Just have underlined here. The refraction of D is larger in the region of larger permittivity, and the refraction of E is larger in the region of smaller permittivity. Exactly opposite, right? So for this equation, when E2 is equal to 1, whenever theta 1 equal to theta 2 equal to 90 degree, right? Whenever we have the tangential components, right? At that time. I hope you will remember these equations. So based on these equations and boundary conditions, we will try to solve some boundary condition problems, right? Okay, first problem we'll take up. Okay, before taking up the problem, just one more formula. We have calculated. We know the relationship between D and P, all those things, right? So by using all those equations, we will get one formula. Actually, this should not come, magnitude. Okay, only take this equation. This is not required. Leave it. If you remember, well and good, no problem. Or else discard it, right? Okay, this should not come. P vector is equal to epsilon r minus 1 divided by epsilon r into d vector. This is the relation. This, please you remember it. That will be helpful in order to calculate the polarization. And epsilon r equal to chi e plus 1. You just remember this equation. This is sufficient, right? Okay. We will try to solve this boundary condition problem. Let region 1 z less than 0 be composed of a uniform dielectric material for which epsilon r is 3.2. Okay, this is region 1. While region 2, which is z greater than 0, is characterized by epsilon r equal to 2. So epsilon r is 3 means region 1 is having higher permittivity. So just let me try to draw the diagram here. Right? So higher permittivity, let me call it as region 1, right? Epsilon r is 3.2. Let me call it as epsilon r1 because region 1, right? So this is region 1. Region 1. The next, where z is less than 0. Z is less than 0. Next, region 2, where z is greater than 0. What about epsilon r? Let me call it as epsilon r2 corresponding to region 2. It is 2. And I have taken the region of higher permittivity above, right? As we have seen earlier. always you take, so that it will be easy for us to write the formulas, always you take the region of higher permittivity in the as region 1 above, right, and region 2 below here. Okay, fine. And one more thing, observe here, if I draw, take x y z axis, observe here, x y z, right. So this boundary, this is the boundary, it is located in xy plane. Z, if I go in this direction, z is greater than 0, but I have taken reverse, right? Z is less than 0, I have taken above, just I have reversed it, that's all, for my convenience, right? So z less than 0 should come below, z greater than 0 should come above, but I have reversed it for my convenience, so that this diagram matches with earlier concepts, right? So I hope you understood this, why I have taken like this. So this is one dielectric material in region 1, this is another dielectric material in region 2 having epsilon R2 and so on. So this is the boundary, right? Okay, let D1 vector is given, right? This is the D1 vector. Then find dN1, dt1, so vector dt1, magnitude d1, theta 1, p1. All these things we have to find out. Okay, just keep this diagram as it is right now. So we will solve. Before solving, we have to derive some conclusion from d1 vector. What is this d1 vector? Okay, so I will write here. Okay, let me write. Okay, I will leave some space for diagram because I will be using it later on. D1 vector is equal to minus 30ax plus 50ay plus 70az nanocoulomb per meter square. Nano means 10 power minus. Let me write it, 10 power minus 9. Put bracket. Right, 10 power minus 9 coulomb per meter square. Okay, every vector, it consists of tangential component as well as normal component. So d1 vector is equal to tangential component d tan 1. Instead of calling tan, simply I can write dt1. So because they have used dt, right, or else d tan, whatever it is, right. So d tan 1 plus dn1, normal component. So this vector is having the tangential component plus the normal component. So this is the total vector given. But in this, which is tangential component and which is normal component? Just have a look at the diagram. See, observe here, this boundary is located in xy plane, right? This boundary is located in the xy plane. Above this boundary, z is less than 0 I taken, right? And below is z greater than 0. Means if this is lying in xy plane, means so x component and y component, this will form the tangential component, right? These two. And normal component, normal to the surface, only z, right? Above or below. So I will write here which is tangential component. Let me, instead of d tan 1, let me take dt1. dt1, so minus 30ax, this is the tangential component, minus 30ax plus 50ay into 10 power minus 9 coulomb per meter square. Then what about this normal component? I will write the remaining normal component. So it is this term, 70az, 70az into 10 power minus 9 coulomb per meter square. If I add this tangential component plus normal component, I will get d1 vector, right? So first part, what they have asked, find out dn1. So already it is done. Dn1 is here, right? So just I want magnitude of dn1, right? So dn1, what is magnitude? Dn1 they have asked. So dn1, just I'll write dn1 once again, 70az into 10 power minus 9 coulomb per meter square. But I want only magnitude. So dn1 is equal to under root of 70 into 10 power minus 9 whole square. So once again I will get the same thing, 70 10 power minus into 10 power minus 9 coulomb per meter square. This is the magnitude, right? Or else simply you can write 70 nano coulomb per meter square. So dn1 you can check it, right? 70 nano coulomb per meter square, right? This dn1 is over. Next dt1, already we have done here without asking only, right? So this is dt1. So for formality you write down once again dt1, what they have asked, dt1 vector, dt1 vector. So what is the dt1 vector? Minus 30ax plus 50ay into 10 power minus 9 coulomb per meter square. So this is dt1 over. Just check it, right? Minus 30x plus 50ay nanocoulomb per meter square, right? dt1 is over. Next, magnitude of dt1. See, magnitude of dt1. So under root of 30 square plus 50 square, 30 into 10 power minus 9. So under root of 30 exponential minus 9 square plus 50 exponential minus 9 whole square. We will calculate the magnitude. So under root of 30 exponential minus 9. Okay, just I'll make use of brackets, open bracket. 30 exponential minus 9 square, then plus plus 50. I'll make use of brackets once again. 50 exponential minus 9 square, 50 exponential minus, close the bracket. So I'm getting it as, just I'll express in terms of nano, was 58.309 into 10 power minus 9 coulomb per meter square, right? Okay, 58 into 58.309, right? Nano coulomb per meter square. So this is over. Next, d1, just magnitude, it's not a vector. d1, right? Magnitude d1 vector we have here, right? This is the d1 vector, right? So magnitude of d1 vector is equal to under root of 30 square plus 50 square plus 70 square, but nano you should not leave. 10 power minus 9 you have to take into account. So under root of, so I'll calculate under root of 30 exponential minus 9 whole square plus 50 exponential minus 9 whole square plus 70 exponential minus 9 whole square. So I'll calculate 70, open bracket, 30 exponential minus 9 whole square plus 50 exponential minus 9 whole square plus 70 exponential minus 9 whole square, close bracket. So after calculating, I am getting it as 91.104 into 10 power minus 9 coulomb per meter square, right? So d1, check it, 91.104, right? Nano coulomb per meter square. So this is over. Next, theta 1, right? So now we will make use of the diagram. E I want, so let me do it here only. So theta 1 is asked, you have to calculate. Okay, so since these two are perfect dielectrics, we know the boundary conditions. What is the boundary condition? dn1 is equal to, sorry, E tan 1 equal to E tan 2 will come here, right? I don't want, just let me take the normal component. What will happen? I just have written here just for to recall, right? So dn1 equal to dn2, yes, it is fine, correct. This is the boundary condition I will going to use. So you can observe here, this is region 2, right? In region 2, what will come? dn2, and in region 1 dn1, right? So dn1 equal to dn2, they will pass, just they are continuous. Normal components of the electric flux density, they are continuous, right? They are not making any diffraction here. But let me take the resultant. So since this is the region of larger permittivity, theta 1 will be more. So this is d1 vector in region 1, d1 vector, right? So theta 1, this is theta 1, right? Then this is the region of lesser permittivity as compared to region 1, right? Theta 2 here, d2, this is d2, and this theta 2, theta 1 is greater than theta 2 because this is the region of larger permittivity. So theta 1 is greater than theta 2. So there is larger refraction of d1 here as compared to d2. I hope you got it. So next, what they asked, theta 1 I want. If I want theta 1, so let me, what is dn1? dn1 is equal to d1 cos theta 1, right? d1 cos theta 1. So dn1 is equal to, by looking at the diagram, I am writing dn1 equal to d1 cos theta 1. Just I am taking the magnitude d1 cos theta 1. I am not taking the vector here. Just I am taking the magnitude. dn1 equal to d1 cos theta 1. So what is dn1? dn1, it is there, 70 into 10 power minus 9. Then what is d1? d1, it is here, 91.104 into 10 power minus 1 cos theta 1. So find out theta 1. Theta 1 is equal to cos inverse of 10 power minus 9, they will vanish, right? So 70 divided by 91 point. So cos inverse of, so my calc is in degree mode already. So if it is in radian mode, please convert it into degree mode before calculation. Cos inverse of 70 divided by 91.104. So I am getting it as 39.79 degree. So 39.79 degree, right? So this is over. Then if I ask calculate d2, same thing, dn2 is equal to d2 cos theta 2. You can calculate, but theta 2 will be less as compared to theta 1, right? That you should be knowing, but it is not asked here. They can ask to calculate theta 2 also. So dn2 is equal to d2 cos theta. Take the projection here, right? So you can calculate theta 2 also. The next part of P1, polarization. F, the polarization P1 they have asked, right? So I told you, remember this formula. This will be very easy, right? So P vector is equal to epsilon r minus 1 divided by epsilon r into d, I think, right? Yes, into d. So just simply we'll take the magnitudes. So here 1 is there. So instead of I'll write P1, just I will remove these vectors and write P1 is equal to epsilon r minus 1 epsilon r1 permittivity 1, because P1 I want. If it is 2, make it 2 everywhere, right? So epsilon r1 into d1. I hope you got it, how to write the formula. So what is epsilon r1? But they have asked vector only, so let me take vector only, right? Because we want P1 vector, not the magnitude. So is it fine? Okay. What is epsilon r1? It is 3.2. 3.2 minus 1 divided by 3.2. Then what is d1 vector? D1 vector is here, minus 30ax plus 50ay plus 70az into 10 power minus 9. So calculate this, that will be P1, that's all, right? So what I will do, I will just simplify this and I will multiply and directly I will write. So first I will do this. 3.2 minus 1 is 2.2. 2.2 divided by 3.2. So I am getting it as a point, this quantity I am getting it as 0.6875. I will multiply and directly I will write, right? So 0.6875 into 30. So I am getting it as 20 point. So minus 20.625 625ax, then plus I will multiply 0.6875 into 50. So 34.375 ay. Then I will multiply 0.6875 with 70. So I am getting it as 48.125 az. So 10 power minus 9 you have to write 10 power minus 9 coulomb per meter square, same as the unit of electric flux density, right? So just cross verify, minus 20 plus 34 minus 20 plus 34 plus 48. Is it fine? So this is correct. This is over, right? Okay, similarly we can calculate this second problem, this one. Yes, the same problem, whatever we have solved is the same problem, this one, but next we'll take up this problem, continue this previous problem, the same previous problem, right? Then here what they have asked, the same previous problem, whatever we have solved, continuation of this, right? Okay, instead of asking what they have asked, instead of asking dn1, we have found out all these things, fine. Next they have asked to find out dn2, dt2, d2, p2, theta 2. We will find one by one, right? So we will take up the same diagram, everything, right? The same diagram, this one, everything, right? I will not draw the diagram once again, I will refer this only. Okay, so first what they have asked, dn2 part A, dn2 vector, right? dn2 vector, fine. Okay, we know the boundary conditions, dn1. So they have taken magnitude, but let me take vector, dn1 equal to dn2. Is it fine? Yes, dn1 equal to dn2. So now what is dn1? Already we have found out here, right? dn1 is 70 az. nanocoulomb per meter square. 70 AZ nanocoulomb per meter square. 70 AZ nano means 10 power minus 9 coulomb per meter square. Over. That's all. Using boundary, you should be knowing what you are doing, what should be used, right? So 70 AZ nanocoulomb per meter square, right? So this is over. Next, dt2 part B. dt2. Okay, next I want this. So how to calculate this? Can I whether I have d2 here somewhere here in the previous thing? No, I don't have. So I can find out how to find out dt2. Let me take. So let me write the boundary conditions, whether it will help me. dn1 equal to dn2. This is one boundary condition. So epsilon 1 en1 equal to epsilon 2 en2. Okay, this is one boundary condition. Then with what about the normal component? d tan 1 equal to e tan 2. So from this I can write with respect to d tan 1 divided by d tan 2 equal to epsilon 1 by epsilon 2. Let me, I want d tan. So I know d tan 1, I know epsilon 1, I know epsilon 2. So I can calculate d tan 2, no, because there was d tan 2 only, right? So d tan 2 is nothing but dt2, right? So let me write the formula. dt2 vector, let me take all these as vectors. dt2 is equal to, I'll take this dt2 here this side, and epsilon this side, right? So epsilon 2 by epsilon 1 into dt1, right? I hope you got how to write from this. dt2, take this side, so epsilon 2 by epsilon 1 into d tan 1. So what is epsilon 2, epsilon 1? So epsilon 2 is nothing but epsilon naught into epsilon r2. Then epsilon 1 is nothing but epsilon naught into epsilon r1, right? So epsilon naught will get cancelled. So into what is dt1? dt1, let me write this as it is. Later on I'll substitute. Okay, what is epsilon r2? What is epsilon r2? Epsilon r2 is 2, right? Epsilon r2 is 2, and this is 3.2 to 3.2 to 3.2. Is it fine? Okay, then what is dt1? dt1, here we have dt1, part B, right? dt1. So this one dt1. Is it fine? Already we calculated from previous problem. I am taking dt1, right? Okay, the same thing you can write. Minus 30ax plus 50ay. Minus 30ax plus 50ay. Plus 50ay. Nanocoulomb per meter square. 10 power minus 1. So you will calculate this. So dt2 is equal to, so 2 by 3.2, and I will multiply and write, right? So 2 divided by 3.2. So I am getting it as 0.625. This one 0.625, I will write somewhere here. Then I will multiply with 30. 0.625 into 30. So I am getting it as 8 minus into plus minus, right? So 18.75 kx. Then I will multiply 0.625 with 50. So it is sign is positive only, plus 31.25 ay. So into 10 power minus 9 coulomb per meter square. I hope you got it. So just verify dt2 minus 18.75, right? Minus plus 31.25 nanocoulomb per meter square, right? Yes, over. Then this is over. Next, d2 they have asked. So part C, what is d2? d2 is equal to, it is combination of tangential component plus normal component. So dt2 plus dn2. So I have dt2 here, and where dn2 here, it is dn2. So just add these two, right? So dt2 I will write minus 18.75ax plus 31.25 ay. 10 power minus 9, I will take it later. dn2 it is 70 az plus 70 az into 10 power minus 9 coulomb per meter square, right? So this is over. Yes, this is over. Next P2 they have asked. So part D, P2, right? So we know the formula P2 vector is equal to epsilon r minus 1 divided by epsilon r into D2. So epsilon r2, epsilon r2. Is it fine? Okay. We'll calculate P2 vector. Vector only they asked, right? Yes, P2 vector, right? We'll try to calculate. So what is epsilon r2? Epsilon r2 is 2. Epsilon r2 is 2. 2 minus 1 divided by 2 into what is this D2 vector? Just now you have written here minus 18.75 AX plus 31.25 AY plus 70 AZ into 10 power minus 9 coulomb per meter square, right? So we'll calculate this, or else we can leave here 2. So just divide by 2 minus 1 is 1, 1 by 2. Just divide by 2, right? So 18.75 divided by 2. 9 point minus 9.375 AX. Then 31.25 divided by 2. So 15.625 AY. 70 by 2 is 35 AZ into 10 power minus 9 coulomb per meter square. So this is over, right? So minus 9 plus 15 plus 35. Minus 9 plus 15 plus 35. This is over, right? Next, this is over. Next, they asked to calculate theta 2. Theta 2. Yes, we will have a look at the diagram. This same diagram. Theta 2 is equal to what? dn, just I'll write the equation here. dn2 is equal to d2 cos theta 2. d2 cos theta 2, right? So I want dn2, right? So take the projection. dn2 is equal to d2 cos theta 2. So d2 cos theta 2. d2 cos theta 2. So what is dn2? dn2, yes, take the magnitude. dn2 vector I have, take the magnitude. 70 into 10 power minus 9. 70 into 10 power minus, this is the magnitude. Then d2 I have here, this is d2, take the magnitude. Under root of 18.75 whole square plus 31.25 whole square plus 70, but 10 power minus is there. So under root of 18.75 exponential minus 9 whole square. So take this. So how much you will get, you will see under root of open bracket 18.75 exponential minus 9 whole square plus open bracket 31.25 exponential minus 9 whole square plus open bracket 70 exponential minus 9 whole square close bracket. So I'm getting it as 78.918. I will write it here. d2 magnitude of d2 is 78.918 into 10 power minus 9 cos theta 2. So 10 power minus 9 they will vanish. So theta 2, keep your calculation should be in degrees mode. So cos inverse of 70 divided by 78.918. So I'm getting it as 27.50 degree, right? So 27.50. Just observe theta 1. Theta 1 is how much? 39. So it is greater. Theta 1 is greater than theta 2, right? Because it is having larger permittivity, right? So I hope you understood these problems. Let me have a look at the time. 3:09. Still I can solve one more problem. Okay. Shall I give it as homework or you will do it? Still I have time. I can. Let me check what is the next topic. Okay, this is the new topic. Anyhow, I'll solve and wind up this, right? Okay, still. Okay, the region with z less than 2 is characterized by epsilon r2 equal to 2 and z greater than 0 by epsilon r1 equal to 5. D1 is given, find D2, Dn2, D10 the same. We'll see one by one. So z less than 0, z greater than 0. Right, z greater than 0, I'll take it above. And it is epsilon r1 is 5. This is region of larger epsilon r2. So I'll take this first. So z greater than 0. Where what about epsilon r1? Epsilon r1 is 5. Right? For z less than 0, what about epsilon r2 is 2? Epsilon r2 is 2. Right? Okay. This is region 1 and this is region 2. Right? Okay, region 1 is having larger relative permittivity or dielectric constant as compared to region 2. And this is the boundary. Right? So observe here once again x-axis, y-axis, z-axis. So this boundary is lying in xy plane. So z greater than 0, yes, it is correct. Now it is correct. In the earlier case, I have taken reverse. So now it is correct, right? Z greater than 0, z less than 0. This is fine. Okay, when this diagram is required, I will finish this. Right now it is not required. Let me continue with this. So d1 vector is equal to 2ax plus 5ay minus 3az into 10 power minus 9 nano, right? Coulomb per meter square. So every vector can be classified into two components, tangential and horizontal. So d1 vector is equal to what? Tangential component dt1. Oh, here they have used tan 1, tan 2. Okay, no problem. Let me write it dt2 only, right? Okay. dt1 vector plus dn1 vector. Is it fine? So this consists of tangential component as well as normal component, which is that we have to identify. So in the since the boundary is lying in xy plane means x and y, this will form the tangential component and this will form the normal component. So I'll write dt1. What is dt1? So dt1 is equal to 2ax plus 5ay, that's all, into 10 power minus 9 coulomb per meter square. So what about dn1? So this one minus 3az, minus 3az into 10 power minus 9 coulomb per meter square. Right, if I add tangential component now I'll get back d1. Right, this is what I have got it. So first what they asked, find d2 part A. Okay, I'll go to the next slide only. D2, what is d2 vector they asked, right? Okay, I have information of d1. What about, let me use the boundary condition, dn1 equal to dn2, right? Okay, let me write in terms of magnitude first. We can, whenever I want vector I can take it. So epsilon naught en1 equal to epsilon naught en2. This is the normal boundary condition. Then tangential e tan 1, let me write the boundary conditions first. E tan 1 equal to E tan 2 and that is equal to d tan 1 by d tan 2 equal to epsilon 1 by epsilon 2. Can I make use of this? Let me check it. Yes, I can make use of this now, right? So what is asked? So sorry, d2 they have asked. Okay, I can find out d tan 2 here from this, no problem. Then let me find out. Then d2 vector is nothing but the tangential component d tan 2 plus the normal component dn2. Is it fine? So call this as equation 1. So you'll find out d tan 2 and dn2. So from this boundary condition, the first boundary condition, this is first, this is second actually, right? This is tangential and this is normal, right? Okay, I want to calculate the boundary conditions. We'll okay, first we'll find out d tan 1. I know d tan 1 is given. Yes, d tan 1 is here. It's fine, I can make use of that. Okay, I want vectors. So d tan 2 I want. D tan 2 is equal to this, from this take this side, epsilon 2 by epsilon 1 into d tan 1, right? So I am taking the vectors now. So what is epsilon 2? epsilon naught into epsilon r2 divided by epsilon naught into epsilon r1 into d tan 1. So epsilon naught will get cancelled. What is epsilon r2? Epsilon r2 is 2 by 5. Epsilon r2 is 2 by 5. 2 by 5 into what is d tan 1? D tan 1 is here 2ax plus 5ay into 10 power minus 9 coulomb per meter square. So d tan 2 is equal to, so just what is 2 by 5 and just I'll multiply, right? So 2 divided by 5 into 2. So I'm getting 0.8 ax plus, so 2 by 5 into 5, 5 will get cancelled, right? So I'm getting 2 only, 2ay, so into 10 power minus 9 coulomb per meter square. So similar, next we'll find out dn2, right? So dn2 is equal to what? dn2 is equal to dn1. So what is dn1? dn1, it is here minus 3az, dn1 minus 3az into 10 power minus 9 coulomb per meter square. So add, so d2 I want, so equation 1 implies d2 vector is equal to d tan 2 is here 0.8 ax plus 2ay plus plus minus 3az into 10 power minus 9 coulomb per meter square. Is it fine? So let me verify. 0.82 minus 3, 0.82 minus 3, 0.82 minus 3. Is it fine? So this is over. Next dn2 they have asked. Already we have calculated dn2. Let me, as a formality, we will write. I don't have a space. Okay, let me write it part B. See, I am doing somewhere wherever space is available. B, I will do it here only. dn2. What is dn2? Already we have found out. So dn2 here it is there. What is dn2? Minus 3az into 10 power minus 9. Minus 3az into 10 power minus 9 coulomb per meter square. This is over. So minus 3az. Yes, they have missed nano, 10 power minus 9 is missing here, right? Unit is coulomb per meter square. Next, this is over. Next, this is also over. So C, let me write this as C. D tan 2. For formality, we will write, that's all. So D tan 2 we have calculated here, right? This is D tan 2. 0.8 ax plus 2ay. 0.8 ax plus 2ay into 10 power minus 9 coulomb per meter square. So here it is, right? So this is over. Then part D we will take up the angle that D2 makes with z axis, right? So z axis will be like this, right? Is it fine? So since dn1, so if I take, let me assume this is region 1, right? So let me take it as dn1 and this as dn2, right? Okay, if I take z axis, this is z axis, right? So z greater than 0 above this boundary, z less than 0 below this boundary. So both z axis and this dn1 equal to dn2, right? This is dn2, this dn1, right? I can make use of this and calculate. So since the permittivity is more, so what they was the angle, right? Let me write. So here theta 1 will be more, this is d1, right? So theta 2 will be less, this is d2. Refraction will be less, right? Theta 2, because lower permittivity, right? Okay, it is, see, the angle that d2 makes with z axis means the angle with, this is the z axis, right? The angle that d2 means here, right? It makes with z axis means with respect to dn2 I am speaking, right? So I want, so I will make use of this. dn2 is equal to, I think this angle will come the same. Let me check it, or else we will go for this. dn2 is equal to d2 cos theta 2. I want dn2, right? d2 cos theta 2, d2 cos theta 2. Okay, let me write it here. Dn2 is equal to d2 cos theta 2. So what is dn2? Where is dn2 here? Part B, dn2. Here it is there, dn2. Just magnitude I want. Minus 3 into 10 power minus 9. Magnitude, right? Under root of this square magnitude, right? So I will get back the same thing. So what is, where is d2? d2, I think here it is there. And this is d2. So now I want only magnitude, right? So magnitude of d2 is under root of 0.8 exponential minus 9 whole square plus 2 exponential minus 9 whole square plus 3 exponential minus. We'll calculate this. How much you will get? See, open bracket, 0.8 exponential minus 9 whole square plus open bracket 2 exponential minus 9 whole square plus 3 exponential minus 9 whole square. So close bracket. So I'm getting it as, just I'll write it here only. So I'm getting it as 3.69 into 10 power minus 9 cos theta 2. Then we'll find out theta 2. So 10 power minus 9 will get cancelled. So cos inverse of, so minus 3 divided by 3.69. I think it should come same. So I'm getting different angle here. dn1 is fine. Sorry, dn2 it is fine. Minus 3 I said. Then d2, I hope I have calculated properly this one. Just to check it. If I made any mistake, please tell me. Theta 2 cos inverse of minus 3 divided by 3.69. So I'm getting it as.
Sir, it is not minus 3, sir.
Then magnitude, yes, plus, sorry, yes, magnitude, right? Yes, thank you very much. This is magnitude we have to take, so it will be plus, not minus. Under root of minus 3 into 10 power minus 9 whole square, so it will be plus only. Yes, correct. Cos inverse of, let me do it plus. Okay, let me check it. Yes, I'm getting the angle now. Yes, see, this minus sign has created havoc. So 35.609 degree, right? 35.678, almost near, right? Next, P2. I hope you will calculate P2 now. I will leave it to you. You calculate P2. Any answer is not given, but let me give the hint how to do it. So P2 is equal to what? P2 vector I want. P2 vector is equal to epsilon r minus 1 divided by epsilon r. Just I am giving the hint. I don't know the answer. You calculate it into just d2 only, right? d2 vector. So this epsilon r2. So epsilon r2 we have here, right? d2 we have calculated, d2 vector. You do it and you will get some vector. This is the formula. Just I'm giving the hint. You do it, right? So I'll stop my today's lecture here.